don't know why those are blue, but I guess they're blue. Okay. So does anyone know the difference between, or does anyone know what a scalar is? So it's not a trick question. It's math. Thank you, Alex. A scalar just means a regular number. So for all of you who say you haven't worked with the vectors yet, what you've been doing all this time is working with scalars. So I'll just write that here so we capture it. A scalar is just a number. So, 5 is a scalar. And a vector is sort of the other thing. So a vector is, I would say it's a combination of a magnitude and a direction. The dynamic duo. Can anyone think of just based off of this definition, can anyone think of something physical that you might describe with a vector? Okay, wheel orientation. So just the wheel orientation by itself, you could describe as a scalar because the wheel orientation would just be one number, it'd be an angle. We've got from Alex the joystick. So yeah, so that's a good example. So if you look at a single joystick that's got an X and a Y direction on it, the value that we're reading from the joystick is both a direction. So right, if you've got your little joystick bubble here sitting in the center, and you move the stick to one quadrant or another, you've got the direction that the joystick is pointing, and you've also got how far forward you're pressing that joystick, whether or not your joystick is currently located here at the center or all the way out here or here or here. So it's the angle and how far it is. You just said that, a quadrant graph. Lindsay, can you clarify that question? I'm not sure I understand the question. Okay, not really. Vectors don't have to be just restricted to a quadrant graph. You could describe parts of a quadrant graph with vectors. What we're showing here is, so we've got our joystick, and I guess my takeaway here, right, is that the joystick position has two values associated with it. It's got its position in the XY coordinate space, like what direction it is. Let me see if I can draw that. Let's do this. So if you've got this joystick position, and then you've also got, I'm not copying, or I can't copy and paste. And you've also got this one. Oh, great, it's red. These both have the same angle position, right? They're both representing the same X and Y, but this one would theoretically be telling them, it's you pushed a lot further on the stick. It has a larger magnitude. Conceptually, does that idea of representing a value with some sort of direction and the magnitude of that value make sense? Okay. So that's all a vector is. Everything we're going to do here is two-dimensional vectors, so vectors that exist in sort of a 2D plane. You can have vectors of however many dimensions as you want. You could have a 100-dimensional vector, and you can still do the same kind of math on it. But we're going to just mess around with 2D vectors for the Swerve map. So one of the ways that you can describe a vector, and there's lots of different ways to write it, but one of the ways is let me do this. Arrow. Okay. Okay, so typically you see vectors drawn as arrows because it's fun. Because you've got to represent the magnitude and the direction. So the direction is the direction of this arrow. Sorry, I don't have a better way to sort of describe that. And then the magnitude, though, is the length of the arrow. Is the magnitude. And then just the direction within the XY coordinate space the arrow is pointing is the direction of that vector. One way that you could describe the vector, so let me say this. Describe. Well, here, let me ask the question. What would be one way that you could describe this vector to someone else? Like if you had to talk over the phone, if you had this vector in front of you and your friend was on the other end of a phone and you wanted them to draw this exact same vector, what would be one way that you might represent that vector so that they can draw that vector on their end? Degree from origin and point of ending. Okay. So let's see. So one option is degree from origin and point of ending. So that's an option. So that would be, just to clarify, Alex, that would be if we took this degree from origin, like this one here, and then when you say the point of ending, do you mean like the coordinates of this point out here at the end of the vector? Yeah. Okay. So that would certainly work. That would define this. It's actually, you're providing actually a little bit more information than you need to provide, because if you give them the actual endpoint of the vector and they know it starts at the origin, they can calculate the angle here, right? You could do the inverse tangent of the y coordinate over the x coordinate, and you could back out the angle. So you actually could define this with just, we'll say, knowing the start and end xy coordinates. Does that make sense? Any questions on that? And then the other way you could do it is you could define it as the degree from origin and the length. So you could also know that this is 5 inches long and 56 degrees in this direction. And that would also be another way to define that vector. Any questions on, does that make sense to everyone? Are there any questions with that? Okay. So now we need to talk about, now we sort of know conceptually what a vector is, we should talk about how we can construct vectors and how we can do some very simple vector math. So if I take, here, let me do this way. Okay. Does anyone have any thoughts? So, right, we've got, if we were doing scalars, we'd have something like 5 plus 6 equals 11, right? This is scalars. Any thoughts on what it would look like physically to add two vectors together? You add the angles and do something on the unit circle. You could probably do that if you want to do it sort of mathematically. Let's look first at it just physically. So here, let's do this. Let me show you this. So if this is the scalar example with math, the equivalent scalar example with sort of physical objects would be, let's make these a little bit different so we can see it a little better. Let's do 2 and 6, and that's 8. So if we just had like a 2 bars of length 2 inches and 6 inches, and we added those together, what would that look like physically? So Alex, let's look at just the scalar first. So Lindsay says depends on how you put them together. Do you want to elaborate a little bit on what you mean by how you put them together?
Ways to put 2 rods together. You can line them up like this, or you can line them up like this. Which way are you talking about?
Okay, that's a fair question. So in the scenario of a scalar, you only have one dimension. You're not even just living in flat world here, you're living in one-dimensional world. So only one dimension exists. So you actually can only stack them. So you actually don't have the physical space to either side. Does that make sense? Okay, so the summation of these two vectors, or these two scalars, is just a larger stack, right? So if you had this one's length 2 and this one's length 6, you get a stack that's a total of 8 tall. What do you think about adding the 2 vectors together? Ethan, any thoughts?
Okay, would you just add the lengths of those I'm just gonna say sticks for all, or arrows together, and then add the angles together, whatever that sum will be, you get your vector.
Which sticks are we adding together?
The 2 arrows below. So the longer arrow, that's going up, and then adding the the smaller arrow going down. So
yeah, so if we
the longer arrow and probably a shallower angle.
Okay, yeah. So you've intuitively arrived at what it's going to look like. If we want to sort of show it graphically, you can do the exact same thing where here you stack the 2 scalars together. Here you can also physically stack the vectors together. Oops. So if you take them from the end of one to the start of the other one, the resultant vector, and I'll do that in green, or actually I'll do that in orange, goes from that original tail up to the end of the other one. So just to make that super clear, that plus that equals that. Does everyone see graphically how that works? Any questions on that? Okay. So the advantage of this is that this also means that any vector can be constructed from component vectors. So you can take a vector like this orange guy right here, and you can define this vector now by vectors that sum together in order to make this vector. So an example of vector, there's an infinite number of vectors that you could have that would sum together to make this one, just like there's an infinite number of numbers that you could choose that can sum to 8. So one example of vectors that sum together to make that one, which I'm choosing because they're convenient, are these two. So that one and that one. So these two red ones sum together to make the orange one. So any thoughts on why I picked these two vectors to do the why I chose these two vectors to define the orange vector?
Both of those arrows are actually scalars since they only have one dimension.
They are scalars, so they only have one dimension. And a little bit more strictly than that, they are scalars and can be expressed with one dimension because they happen to line up with the coordinate system that we chose. So if we had a rotated coordinate system, the arrows look a little bit different, but right, these line up with are in the same directions as the x and the y on our plot on our coordinate system. And so we can put that vector back there, and we can see that just how Alex suggested from the very beginning, that if we know the end xy coordinates, we can define a vector here. If you look, let's see if I can. These two vectors that these two component vectors are the x coordinate and the y coordinate. Right, their magnitudes, their scalar values, are the x and the y coordinate. They're the same as, right, as this. And so we just came back. We started with vector addition this time, and came back to what our intuition said about how we could define the vector. And Lindsay asked, so like rise over run, exactly like rise over run. So so rise over run describes the slope. In that case, the slope is a single number because it basically is just the angle. Here we're describing both the slope, which is the angle, and we're also, since we sort of care about the absolute values of the x and the y, we're also describing the magnitudes too. So we get a little bit extra, but yes, exactly like, or very similar to rise over run. Are there any questions about anything that we've done with the vector addition, or how we describe vectors? Okay, so the reason we have to talk about vectors is because one of the physical things that you describe with a vector is velocity. So sometimes in how we speak colloquially, how we speak to each other, we say that velocity equals speed, that it's the exact same thing. We use the words interchangeably. In physics and in engineering and everything, velocity should not be used interchangeably with speed. So velocity is actually defined as the direction that you're moving and the speed that you're moving in that direction. So strictly speaking, the speed of your car is the magnitude of your velocity, and what direction you're going, east, north, south, west, is the direction that you're going. And so your car's velocity is the combination of both your car's speed and the direction that your car is moving in. And when we're dealing with a swerve drive, what matters here is the velocities of each of the wheels, the speed that each of those wheels is spinning at, and the direction in which those wheels are pointed. And it's very convenient to describe both of those items as a single vector, being which is the velocity of that wheel. So if we've got our swerve robot, which is going to be pink here, and we've got, let me actually make it not square, and we've got our swerve wheels. Can I make them? I rotate it. I don't know that I can make a rectangle on an angle. Here, let's try the following. I'm a little bit more used to what I can do in here. So I'll keep this and just sort of set that off to the side. Oops. And then just try and switch over to this so we have some more options in terms of drawing here. Okay, so that is our swerve robot. And this is going to be one of the swerve module wheels looking down at it from above. Okay. I'm just going to move into some kind of weird orientations. Okay. So we've got our swerve modules. And before we go any further, I'm just going to remind everyone, I think we did talk about this last time. The numbering scheme that we have is that this is module 0. And then we've got module 1, 2, and 3. We'll refer to those later. Okay. So the velocity of this wheel at any given point in time is going to be pointed in the direction of that wheel, and depending which way the wheel's spinning, the arrow could either be pointing this way or 180 degrees, or be pointed, back the other direction. Okay, so this is wheel velocity. Oops. Choose that one right there. Let me check that. Okay. Does anyone have any questions about defining the wheel velocity? Okay. So the physical question that we have to answer for ourselves, I guess the goal of the code that we want to write, is we need to figure out what wheel velocity we should have for each one of the 4 wheel modules in order to perform any of the driving actions that we want. So let's start out with a simple one. If we wanted to drive the robot forward, and we're going to define forward as being the top of the screen, what orientation should, what should the velocities be for each of the Swerve modules? Alex, what do you think? All right, mystery person, what do you think? Okay, so let's see, Juliana, where do you think the wheel vector should be, the wheel velocity should be if we just wanted to drive forward? That's the question.
Okay, they should all be facing straight, and the speed should just be whatever speed we gave it. So that would be interpreted directly by the joystick.
Okay. So something like that, correct?
Yeah.
Okay. And I'll ask one more simple one. What if we wanted to go to the left?
They should all be facing like 90 degrees.
Okay. So now, we could probably write a pretty simple piece of code that would allow us to do translation of the robot in any direction that we wanted. I mean, really all we need is, if we've got our joystick bubble here, if that's our joystick bubble, all we would really need is to look at the angle, look at the angle of where the joystick bubble is pointed, or in the sort of the XY quadrant of the joystick, and just point the wheels in that direction, and then look at how far the joystick's been pressed in order to know the wheel speed. Right. So if we had, if this was the joystick position, maybe we would turn all of our wheels so that they would look like that. And that would solve the translation problem. Does that make sense to everyone? Okay. So the challenging part of the math comes from the fact that we don't want, in order to fully utilize a swerve, we don't want to just translate. We also want to be able to rotate. And even more crazily, we want to be able to rotate while we're translating. And so we've got to find the answer to the question of what direction should all the wheels be pointed in, how fast should they all be going, in order to both translate in a direction and rotate in any amount that we want. So we still have this joystick here in this orientation, so we want to translate this way, but we also wanted to, let's say, rotate. Let's say that we wanted to rotate counterclockwise. I'm going to go ahead and make some more arrows here just so we have them. Does anyone want to just think about it? There's multiple, you're not going to get an exact thing. Then we want to think about what the wheel orientations might need to look like physically in order to both translate in this direction and also rotate in the counterclockwise direction. So Lindsay says wheel 2, 90 degrees cockeyed. So like if we took wheel 2 and did, oops, Something like that. Is that what you're thinking, Lindsay? Yeah, it would. So certainly this solution, I think, would translate and would rotate the robot counterclockwise. I think you're right that it would not pivot about the center of the robot. I'd have to think some more about exactly where the pivot center would be located in this configuration, but this would at least solve the problem of translation and rotation. We do want to be able to control our center of rotation, so we'll talk about that a little. I guess what I should also say is, let's see, wheel 2 arrow should be facing the other way. Counterclockwise. No, I did say counterclockwise. So this I think would translate a little bit this way, and it would start rotating a little bit counterclockwise. Another way to sort of think through this problem is that right here in this example, we have, I guess, the ideal, let's see, I'll clear this. We have the ideal translation solution. There's also an ideal rotation solution, right? So if we wanted to rotate counterclockwise, that ideal counterclockwise configuration would look something like, does anyone have any questions or comments about how this would make the robot, this configuration would make the robot rotate counterclockwise? Okay. So the sort of, I guess I'd say the final solution to, or the combined solution of both translation and rotation is going to involve a summation of the rotation solution and the translation solution. So we're going to have to find a way to combine these two different solutions. And basically what we're going to end up with is a vector addition problem for each one of the wheel modules that we'll have to solve in order to get the vectors at each wheel module that are the combination of the solution, the combination of the optimal rotation solution and the optimal translation solution. Does that sort of make sense? Any questions on that before we go forward? Okay. So let me go ahead and I'm really like doing that. I'm really liking doing this in PowerPoint instead of with the drawing tools here. Okay. So here is my proposal to all of you. Here's what I'm going to suggest, or claim. I'm going to call it my claim. Is that this vector here, that is the vector describing the wheel velocity, can be made up of two components, any two components that we choose. And we could choose components like we did before where, and also, oh, before I forget, we did decide that our coordinate system was X is this direction. Oops, I almost forgot. And Y is this direction, just so we remember. So we could certainly choose components that are made up from X and Y. However, my suggestion is that instead of choosing those vectors as components of the wheel velocity vector, we instead choose, we instead, I guess I'd say, tell ourselves that this wheel velocity vector can be split into the velocity vector that translates the robot and the velocity vector that rotates the robot. And so we could have two other ones, maybe something like that, and this, which also sum to make this vector. Let me just make these a different color. But instead of them being, x, y components, they are instead let me make sure I got my nomenclature I'm going to use for the rest of this correct. It's going to be very hard without a pen. B R plus VT. Oh, sorry, let me do that again. Sorry, 1 second. We'll call this one, so I'll make sure I'm consistent with everything I do tonight here. B sub T and T sub R. So this is the vector that is this is the component of this vector, or the red vector, that is responsible for the translation of the robot in a given direction. And this is the component that is going to help rotate the robot. Typically, so these are both vectors themselves. They're not scalars right now. Sometimes you see a little arrow drawn above the number, the letter, in order to indicate that it's a vector, not a scalar. We don't have the really ability to do that in PowerPoint easily. The other thing that you'll see sometimes in papers is that they'll bold the character in order to identify that as a vector. So scalars will be not bolded and vectors will be bolded. So I'm going to use bolded here just so that it's so I don't have to draw little arrows at the top of all of the vectors. Are there any questions or comments about the idea of this vector being a summation of being able to define the red vector as the summation of the translation vector and the rotation vector? Let me just write that a little bit more explicitly. Oh my goodness. I have all sorts of problems there. Okay. Wheel. So W is wheel, V is translation, and R is rotation vector. Okay. So let me take a look at the next thing I want to do. Okay, so let's do the following. So we're going to take a look at how we now define the translation vector. So we're going to look at the translation vector and the rotation vector, each in parts. So the translation vector here can be broken down itself. It's a vector. It can also be described by components. And in this case, I'm going to go ahead and describe this one in terms of the XY components that make it up. So this is velocity translation Y component. And this one is velocity translation x component. So we're just breaking this one down further. Now, so this equals okay. So that equals this vector plus that vector. Yeah, so the history person is identifying or reminding us that Alex got the x and the y backwards in code. That is correct. So I think, I don't remember how we ended up fixing it. For a while, it was fixed just by rerouting the wires in the code. I think in the current version, it is actually fixed, where x is this direction, y is this direction. There was a backwards, it was reversed between what we did on the board and what we did in the code. And this system should match it up with the autonomous, and I think how we did on the board. And the current code is set up to handle it in this direction. So, excuse me. We've got the translation vector broken down by its x and its y component. As we sort of talked about earlier, the x and the y components are scalars. They can be described as, right, because they are all in one direction, right? So you could describe them as not bolded v ty or tx plus not bolded v ty. Now, in order to be fully appropriate, we do still need to have information about the direction here, because we are still summing these together to get a vector. And the way that is done with something called a unit vector, and I'm going to have a lot of people drawing that here. Oops. So, bear with me for 1 second. Oh, they have the shape I need. Bear with me for 1 second while I do this. Okay, so the challenging part here is that unit vectors are described, are written down with the letter and a hat. And I know it was kind of weird for a second. Let me show you, now that I've sort of written what it looks like math-wise, let me show you physically what the unit vectors represent. So if we have our coordinate axes, we have two axes, the I hat axis and the j hat axis. And in case you're noticing it right now, I lines up with x, or I refers to x, and y refers and j refers to y. So those go together all the way. That's the standard. The vectors themselves are special in that if I take a, oops, I take the vector, they have a length, they always have, a length of 1. So there's that one, and there's that one. And I guess the way you can look at it is, this coordinate here is going to be, if it's x, right, it's 0 in the y, 1 in the x. And this one is the opposite. This one is, that coordinate at the end is 1 in the y and 0 in the, or sorry, I just do this backwards. 1 in the x, 0 in the y, 1 in the 0 in the x, 1 in the y. So the unit vector is these little green guys here. And so what we have is we have two scalars, the magnitude of Vtx and the magnitude of Vty, multiplied by something that doesn't have a magnitude, but its magnitude is 1. So if you multiply the magnitudes together, you still end up with 1. And its only job is to represent the direction. So this is the magnitude of Vtx in the x direction, and the magnitude of Vty in the y direction. And so it's another way to write Vtx, the vector, plus Vty, the vector. Are there any questions or concerns about this use of unit vectors and splitting things down into a scalar and a unit vector? Okay, awesome. Okay. So the next cool thing that we can do is this approach allows us to do the math part of the summation. I should have shown this before, I guess. Do the math part of this, but I forgot. Do the math part of the summation in vectors. So if we've got that, oops, the velocity of the wheel equals the summation of these two vectors, you could also do the following. You could say that the velocity of the wheel in the x direction I really wish I could draw. The velocity of the wheel in the x direction would equal the velocity, the x component of the translation vector, plus the x component of the rotation vector, which we could also write as, I'm just going to grab this because it's easy. At R, and you can have the exact same thing. Oops. For the y part. So you have the y component of the velocity equals the summation of the y components for the translation rotation vectors, which you can also then split down into their scalar components and their unit vectors. Oops. Okay. So before I ask if there's any question, let's plug in some actual numbers so we can see what that kind of looks like. So if I will do my best to try and keep this looking to scale here. So if I've got two vectors, I've got this one here, and then another one, which is like that. Okay. And I say that the x component of, let's do this. Okay. And I want to add them together, right? So the goal is to add them together. We know from graphically that we could add them together graphically, and we would get this vector here. Right? So we already did that. If we want to do it math-wise, what we could say is that let me just get rid of that. The x component, so I'm just going to say that this one is the translation vector and this one's the rotation vector, and this is the wheel velocity vector that we're trying to get. We could say that, the x component of the translation vector, I don't know, I'm going to call that a 5, roughly. And then the x component of the rotation vector, sorry, let me do that backwards. This is, I rotated myself again, I apologize. That is x, and that is y. So the x component of the translation vector, we'll call that 2 or something. And then maybe it's only 1 for the shorter vector here for the rotation vector. Now the y's are actually kind of interesting because they're negative, right? Positive y is to the left, and both of these vectors happen to be pointing to the right. So for that longer translation vector, we'll call that -5 in the y, and then we've got maybe -1 in the y for the rotation vector. And so what we would end up with is, that's terrible. We would end up with a vector that is 3 in the x, and -6, oh my goodness, -6 in the y. And if we were to just draw that, right, so we would come over -6 in the j, and we would go up 3 in the y, in the x, we would get that same vector that we got just by drawing the two, drawing them graphically. Does everyone sort of see how the summation of the individual components works and how that compares to graphically drawing the vectors? Are there any questions at all before I go on? Or comments? Okay, sweet. So, the green and the red because I use them later. Okay. Okay. So I'm going to go ahead and propose that we already know how to calculate that VTX and VTY are actually pretty easy for us to do. I'll show in a little bit exactly how, is there no highlight function? So I'm going to color them green. I'll show how to, there's going to be some other nuances, but really the X and the Y portions of the translation are just going to be the X and the Y's of one of our joysticks, right? They're describing what direction we want to translate in. So they're going to come mostly directly from there. So we can calculate those pretty easily. The question that we sort of have remaining is we still need to calculate the rotation components in the x and the y direction. So what we need to look at, or what we care about, so if this dtx and dty are the velocity that we want the robot to translate with, that's sort of that's a physical description of the robot that makes sense to us. Describing the velocity that we want to rotate with in terms of its x component or y component is not physically very useful. It's not very physically intuitive to us. A more useful description of it is saying that we want the robot to rotate with a certain angular velocity. So we want it to spin about, the center of, we want it to spin about, the center of the robot with some rotation rate. Let's see if I can. Sure. Okay. We want to rotate about the center at some angular rate. That's sort of the velocity that makes sense to us. And sort of the standard for the letter standard for that is an omega, or as Alex prefers to describe it, an omega. So we've got we want to describe the rate of rotation around the center as some omega velocity. Our challenge now, or our task now, is if we're going to describe omega, if the drivers are going to set omega, we need to convert omega into VRX and VRY, because that's how we need those two, because that's what the Swerve modules are going to need in order to get their final velocity vector. So must say omega. I'm going to stick with omega. Alex, you can say omega in your head if you'd like. So let's see here. What I want to do next. So if we go ahead and look back at this figure where we're just rotating, we're not translating at all. We've got this. Let me ask this question. If we've got these wheels that are all turned at a certain angle to make us just rotate, what about the wheel position and orientation will control how fast we spin around the center of the robot, how fast our omega is? That's a question for you all. What are the things that, what things about the wheel control how fast we're going to rotate about the center of the robot in this figure? Okay, so Alex got the easy one, the speed of the wheel. What's another thing?
The orientation, because if we're turned farther out, wouldn't we spin more slowly?
Okay, yeah. So if the wheels were not as close to the perfect as they should be, right? If they're like this, closer to that, you're gonna spin more slowly because more was going to go in the translation. Is that what you're saying?
Yeah.
Okay. There's one more. So this is a question for Adam. How do you think the behavior would change if the Swerve drive was on a smaller robot, if the wheel was closer to the center versus if the wheel was very far away from the center? What do you think, Adam? Smaller diameter equals less speed, and presumably large diameter equals greater speed. So he's right. So if you're putting your wheel very far away from your center of rotation, you're going to end up rotating at the center of the robot a lot faster than if your wheel was hanging out very close to the center of rotation. Does anyone have any questions or thoughts about that concept conceptually or physically? Okay. So the things that we care about are, we know we need something to describe the distance, which I'm going to call a radius. Oops, that's beautiful. Okay, so we've got some, there we go. And we're going to call that radius. We'll use capital R since we're using lowercase r for the rotation vector. So our angular velocity is going to depend upon this velocity vector, both its magnitude, how fast you're spinning the wheel, and also its direction. And it's going to care about the distance from the center of rotation out to this vector location. Now, if we were going to do a full vector math course, this is where I would say, okay, the radius is actually also a vector, right? It's going from the center to some other point. It's got a direction, it's got a magnitude, right? And in order to find out the interaction between, in order to find this interaction between the radius vector and the velocity vector, we would need to multiply our vectors. And specifically, we need to do what's called a cross multiplication. And you will all cover that at some point. There is a simplification that we can do here that allows us to not actually have to explicitly do the cross multiplication, because we can intuit the answer to the cross multiplication. So let me ask the following. If our wheel is rotated like that, and so it's let's say, trying to think of a good way to do this. So let me simplify this diagram just a hair. So now we have the famous two-wheel swerve. And we're still rotating counterclockwise in this orientation. And we still care about this value R. Do we all agree that if I move this wheel further out, we should rotate faster? What if I do this? Do we rotate any faster? What do you guys think? And assume that I'm doing the same thing to the other wheel. I'm just too lazy to also move the other wheel. So it is symmetric. So let's do a simplifying. Let's look at this even simpler. Let me put our two-wheel swerve like this. Are we currently rotating? Is the robot currently rotating at this point?
No.
Okay. What if I make the radius really big? I bring this back out again. Do that. I've made the radius really big. is, are we rotating the robot?
Is it symmetric? We still wouldn't be, though.
Yes, yeah, it is symmetric. But yes, you're correct. Even if it wasn't symmetric in this configuration, we would not be rotating the robot. So what this is telling you is that it's not just the magnitude of that radius that matters. There's something else that matters too. And that's this relationship between the directions of the velocity vector and the the radius vector. And so let me go backwards in time and ask this question again. And compared to this, are we now rotating any faster when I move the wheel up here?
No.
No, exactly, we're not. Because what matters, the portion of the radius vector that matters is the part that is perpendicular to the velocity vector. It's this part right here. And as we move the wheel up and down, we don't change this distance at all. Whereas if we move it out, we are changing this perpendicular distance, this distance where you get if you do a 90-degree between the velocity vector and the radius here. That one does change, and so we do have an effect on how fast you're rotating about the center of the robot. Does that make sense? Okay, awesome. So the really cool thing about this is we do the following. If we put our robot back into a more normal swerve configuration, I can still the famous two-wheel swerve, but maybe a little bit more normal here. For argument's sake, all of our vector right now is going into rotation. We've got our radius, and because we haven't covered, well, here, let me ask this question. What do you see that might be unique about this radius vector and this velocity vector in this configuration where 100% of our velocity is going into a rotating robot? What is this? What does it look like when you're comparing this vector here of the radius to the velocity vector? How about what's the angle between the radius vector and the velocity vector in this configuration? Alex? Same. So like in degrees, what's the angle between the red vector and the yellow vector? Not 45, 90. There we go, 90. So the key concept, which we got intuitively originally, is that when we turn the wheels like this, the radius out to them is perpendicular to the velocity vector. So all of your radius and all of your velocity are being used to rotate the robot. And we got to that intuitive, like the human brain knows that if you want to rotate something by its center, you sort of turn the wheels to 45-degree angles, sort of make them at these angles. And if we were to make this very non-rectangular, it wouldn't be 45, but you sort of know to turn them at these angles. And what we can see is that outcome is also shown when we do the math too. Does that make sense, or are there any questions about this interaction between the radius vector and the velocity vector? Okay. So the other neat thing is, say that we don't have a perfect situation here because we are actually doing some translation. We've got the same radius vector that we've had, right? It goes out to the center of the wheel here. But now our velocity vector is off at some weird angle. The cool part is that if we describe our rotation, the component of our vector that is supposed to be handling the rotation of the robot, in terms of x and y, in terms of x and y components. I won't put those there, but so if we determine in terms of x and y components, it's a little bit easier for us to look at to see what the perpendicular distance is between this one and this one and this. So if we've got the dimensions of the robot here, so we've got some width of the, oh my goodness, some width of the robot. And some length of the robot. Does anyone know what sort of the perpendicular distance is from the center of the robot out to this x component of the rotation velocity vector? I see Amelie hiding out on here. What does Amelie think?
Sorry, I was adding the picture to the document. What was the question?
It's okay. The question I had was, if we know the width and the length of the robot, what would be the perpendicular distance from the center of the robot out to this x component of the rotation vector?
Half of the width.
Yep. Yeah, half of the width. And then similarly, what would be the perpendicular distance from the center of the robot out to the y component of
the length?
Half the length, exactly. Does anyone have any? Does that make sense? So if I have, we do the following. Right. So you've got that one. You've got that one, right? So that's that distance out to there. And then that's that distance out to there. Does anyone have any questions about that? Okay. So at this point, we're very close to having exactly what we need. So if we recall, the things that we were trying to still find were the x component of the rotation vector and the y component of the rotation vector. So the let's see. There is a conversion between what we call, so there's a conversion between the angular velocity here and then this velocity out here on the red vector. Something I should have mentioned earlier is this velocity along the edge is also often referred to as the tangential velocity. So there is a relationship between the tangential velocity and the rotation velocity, and it's pretty simple. It is the tangential velocity equals the rotation velocity times the radius out to it. And more strictly, we would have the x component of this tangential velocity is equal to the rotation times the radius, the perpendicular radius in the x direction, or sorry, the y direction. Y direction, and then the y component of the tangential velocity is equal to the product of the angular velocity times the perpendicular distance out in the x direction. So let me write that out for you. So that equals, let me get an omega. Equals omega times the perpendicular radius. Okay? And for our purposes, that means that it is omega times, let's see, the velocity in the x direction. The distance that we care about is this one, which is 1/2 the width. So 0.5 times the width of the robot. And then the very similar one, ERY, would be omega times 1/2 of the robot length. And so now we should also have these two values as well. Does that make sense to everyone? Are there any questions? Okay. So we now have a way to get to all of the components of the wheel's velocity vector. If we have time, I'll talk about how we then convert the wheel's velocity vector back into an angle for the azimuth motor and a speed for the drive motor. But before we go too far, we should talk about how we get VTX and VTY and omega from our joysticks, because that's really what that's where our information is actually coming from. So let me switch my notes here to a different set of notes. Okay, so Adam, do you remember if it rotates on the right or the left stick? Left. Okay. So we have, okay, well, we'll pretend it's on the left. How about that? We have two joysticks on our gamepad. And just because life isn't easy, we do have the problem that, oops, go away. we do have the problem that their x and y's are different. Their x and y is oriented like this. So we'll have some fun with that. So I'm going to call this J sub x. So this is, and this I'm also going to call this. I'm going to call this joystick L. Oh my goodness. Oh, x. J2 is rotation. Yeah, I don't remember which way. I remember which one's joystick 2 and which one's joystick 1 is the problem. So we'll just assume that this for tonight. And this one is controls rotation. And this one controls translation. Okay. So oops. The way that we chose to do it, and there are different ways that you could do it. The way that was chosen was that for the translation, or sorry, let's do the rotation first. This omega that we care so much about, we just said that omega was directly decided by the left joystick's x direction. So doing this on this joystick up and down doesn't do anything. Moving it to the left or to the right, though, will make it spin about the robot center faster or slower. Does that make sense? And then we decided as well that the x component of the translation vector is not a vector there. Was equal to the right joystick's y direction, again, because for the robot x is forward and back, and left and right is y. And then similarly, we've got the y component of the translation vector is equal to the right joystick's x direction. Now, there are also some negatives in there that we had to be careful about because the positive and negatives don't line up for some of these cases. And I don't remember which way is which, so I won't try and correct for that here. Does that make sense? Or are there any questions about that? Okay. So just so we can sort of see the final solution all in one place, let me do the following. So so we've got here the x and the y components of the wheel vectors, or the wheel velocity vector, and that equals vtx, which is j, the right joystick value in the y direction, plus, we decided it was omega times 0.5 times the width of the robot. And omega is equal to j left. Oops. And omega is just the left joystick in the x direction. And then we do still have our unit vector in the x direction I. I'm just going to highlight in, let's say, I'm going to highlight in green here. Oh, I guess I can't do that. Let me do highlight in green here. These are the values that we're getting that we know, right? That's the width of the robot. We know the width of the robot. We know the right joystick values, and we know the left joystick values. And then we have a very similar expression for the y component. So this is our x, and this is still Lx here, but this is the length of the robot instead of the width of the robot. And so we do know everything that we need to know in order to solve these equations. Are there any questions on that? Okay. So let's see here. Oh, so I have made the mistake that I missed here. So let me, well, okay. More explicitly, I didn't mention something that could matter. When we do the summations here, and we include omega, when we replace VR, the VRs with the omegas, we do have to watch the signs of the omegas. So if we're looking at omega, positive omega is in this counterclockwise direction. And what we need to be careful about is if we've got a if we're at wheel module number 0, if we've got a positive if we've got a positive component in the x direction, do we rotate counterclockwise or clockwise? And so that's not as confusing. I'm at wheel module 0, and I've got this vector, so in the positive x direction, and I'm rotating counterclockwise or clockwise. Lindsay, what do you think? How about you, Alex?
Could you point to which vector again?
Yeah, of course. Sorry, I've got like a whole bunch of, it is this one that I just made really big. So if we've got this vector here, is it going to cause the robot to rotate clockwise or counterclockwise?
Are all the other wheels moving with that other diagonal one?
Yeah, so just ignore the other wheels for a second and just look at this wheel.
It's moving straight.
So imagine there's only, imagine it's our famous one wheel swerve.
So it's gonna move.
It'll certainly move. There will be some translation, but there's also going to be a rotation part of it. Is it going to rotate? Is the part of it that's going to rotate can be counterclockwise or clockwise?
Is it gonna be counterclockwise?
It is, yeah, exactly. I mean, you can sort of imagine that if you just had, you know, if you just push on the robot in this direction with just that corner, the robot would sort of shift in the counterclockwise direction. So that means that the positive x direction is lined up with the positive omega direction. And so this positive is okay. We have a similar case where if we are looking at this vector, that's the positive y direction, that also causes us to rotate counterclockwise. And so we also have a lineup between, or an agreement between the positive y direction and the positive omega direction. And so we can also have a positive here. Now, this solution that we have in the green box is for this wheel module 0 specifically. Because, let me ask this the same set of questions for wheel module number 1. If we look at wheel module number 1, does this vector make us rotate clockwise or counterclockwise?
Clockwise.
Clockwise. So positive in the x here agrees with a negative omega. And so we would need to swap the sign when we do this summation here. Now, if we did it, now this vector in the y direction, that still gets us spinning in the counterclockwise direction. So you'd only, for wheel module number 1, you would only flip one of the signs, and the other sign would stay positive. Does that difference in the signs make sense? Conceptually. Okay. Now there's also another difference here, which is that if we're looking at this vector on wheel module number 0, the distance that matters is the robot length divided by 2. Now, if we instead look at, let me see if I get this right. One second. Let me make sure I don't say anything wrong. Oh, no, that's fine. Okay. I was just making sure that nothing else changed. So sort of the difference that we see as we go from wheel module 0 to any of the other wheel modules is the signs. The cheating answer is that if you were to calculate this solution for all 4 modules, one of the modules would have the solution that you see here. Another module would have this solution. Another module would have that one. Another module would have that one. And so there's just a sign difference as you go around the perimeter of the robot. There may also be, I have to spend some more time to look at this, for a square robot where L and W equal each other. That's all that would change. In a rectangular robot or in a more complicated configuration like a 3-wheel swerve, you would also have to deal with some changes in the distances that are here. But in our case, L and W are the same for our robot because we have a square base. Does those sign differences as we look at the different wheel modules make sense? Or are there any questions? Okay. Let me see. I think that's the main thing. So, okay, so that describes everything about how we get from the joysticks to these velocity vectors. Now, we still have the challenge of taking the velocity vectors, which is how we describe everything in math really conveniently, and converting them into an azimuth angle for the swerve module, and into the actual speed that we should be spinning the wheel at. And so we've got to do one more set of steps in order to do that, conversion. So we're looking for an azimuth angle and a magnitude, and a velocity magnitude. Let's see. Does anyone want to take a stab at how we would calculate? So let me do this real quick. Two things that we're looking for here are the drive motor speed and the azimuth motor angle. So for wheel module number 1, which we've got the solution here for, does anyone want to think about how we would calculate the speed that we should be going at?
Am I allowed to look at the code I wrote?
I'd like you to think about it conceptually first before we looked at the actual code. So if you wanted to calculate the magnitude of this, do you remember how we did it?
There was a lot of decimals. We did a lot of stuff with decimals and square roots and stuff.
I don't remember a whole bunch with decimals. There are square roots. So if you wanted to calculate the length of a line that someone gave you, and they gave you, the x, y coordinates of the endpoint, how do you calculate the length of that line?
Y2 minus y1 squared plus the x2 minus x1 squared all over under a square or something.
Yep, that's absolutely correct. What does x2 minus x1 represent physically?
The distance. Oh, the Pythagorean theorem. That's what I just said.
The Pythagorean theorem, and as Lindsay said, and as you just also alluded to, those subtractions are the delta y and the delta x. Those are the x and y components of that line if you describe that line as a vector. And so you can calculate the wheel speed that you need as the square root of, it's not supposed to be bolded. The x component squared plus the y component squared. Oops. And that's just the Pythagorean thing where this VWX and VWY are your delta x and delta y. They are those two components of the line. In this case, the line is the velocity vector. Any questions on this equation? Okay. How about taking a stab at how do we calculate the azimuth angle for the motor? So if we've got okay, I'll get an example here. SOHCAHTOA, okay. Yeah, TOA. Can you remind? I have not used the SOHCAHTOA acronym in a while. Can you remind us what TOA is?
Tangent.
Tangent. There we go. So specifically, we can do the inverse tangent of the y component over the x component in order to get the angle. So that everyone can kind of get on that same page here. I grab an example coordinate system. Excuse me. that is my wheel, this red one is my wheel velocity vector. In order to calculate this angle here, oops, that's not what I want. In order to calculate this angle here, I don't know what I did. There we go. In order to calculate this angle here, we can do the inverse tangent of the y component over the x component. So we would have arctangent, which is just another way to say inverse tangent. They're completely identical, of the y component of the velocity divided by the x component of the velocity. Does anyone have any questions about that set of equations? Okay, so from the equations in the two green boxes, we can convert from our three joysticks that we have, our two joysticks each with the three joystick values that we're pulling from the gamepad. We can convert directly from those into the wheel speed and the azimuth angle for wheel module 0. And we can do a very similar solution for wheel modules 1, 2, and 3. Are there any questions about anything that we've covered up to this point? Okay, so before we make sure we see where we're at on this. Yes, okay. So the last thing I just want to talk about is I want to ask you guys a question. And Alex, I'll go to you at the end if no one else can remember since you wrote it. What could be a potential problem with how we've added together the joystick values here? There's actually a couple specific problems. So my first question is a units question. Oh wait, here we go. Why not all of it multiplied by the point? Can you, so Lindsay, can you clarify that question a little bit?
Based on the order of operations, the only things that would be, the first thing would be j of Lx times 0.5. So wouldn't they all do that? Would it have the same answer? Because it would multiply differently?
I think we're okay on order of operations. Typically, if we were to write it exactly like this, we would multiply the j times the 0.5 times w first, and then we would sum it to j r y. So I think we're okay on order of operations, but that's something that we always want to check. Any other thoughts as to some problems? I think there's basically two. So let me ask you about the units. What units is W in? Adam, what units do you think we measure the robot in? That wasn't supposed to be a trick question. Inches, okay, Lindsay says inches. So W is in inches. what are the units of the joystick values? They could be in degrees. Basically, that one's sort of a, okay, so velocity. So it's sort of a little bit of a trick question. The joystick values as they are don't have a unit. They go from -1 to 1, and they're unitless. And so if we were to directly apply this formula, we would have this problem where we're not really allowed to add, a unitless number to a number with units, right? If we measured the robot width in inches, we would get a different answer than if we measured the robot width in feet, even though they're both, the correct, even if they're both correct values. And so we have two options. So the first option that Lindsay suggests is we could convert the joystick values into velocities. So instead of it going from -1 to 1, it would instead go from -20 feet per second to +20 feet per second, and or the equivalent of that in inches per second. And that would be totally valid, and that would be a better approach than what we're doing right now, and it would sort of go back into what we talked about last session about, instead of setting a power on the drive motors, setting a goal speed. The option that we chose to go with was to do a normalization of what we call a normalization of these dimensions, so we get rid of the units. And what I'll do is I'll show you how we did that in code, probably next session. I won't get into it today, but basically we end up just dividing stuff out, and it ends up not being too big of an issue. It's still not as good as it being in velocity for reasons that we can talk about some more later, but it does at least solve the unit problem. Now there's another issue that is really critical about these additions. Does anyone have any thoughts about that? So what happens if I am the driver and I am being yelled at by Dr. B to score 17 balls in the next 12 seconds, and so I just push all of the joysticks in all of the directions possible, and so I get a full power on the translation joystick, and I get a full power on the rotation joystick. What is the robot? What happens to the robot physically in that scenario?
Wouldn't it just do nothing?
I don't know that it would do nothing. You would have an issue. Lindsay asked about feedback node error problems. I don't know that there would be a specific issue with a feedback node. What you do have is, if your maximum translation power is 1, like +1, and your maximum translation power is a 1, yes, we have these additional multiplications in here, but you're going to get a number that is greater than 1 here, and you're going to add it to a 1. So you're going to have and then you're going to do the squares, the squaring, and then the square root. And you're going to have a drive motor speed that is larger than 1. But 1 is the largest amount of power that you could send to your motor. And so you're in this scenario where you've asked the robot to do something that it isn't physically capable of doing. And what that's going to look like is you're going to lose orientation control of the robot, because all of a sudden, it'll say that, this wheel needs to go at a power of 1.5, and then this wheel down here needs to go at a power of 0.9 or something in order to do the exact rotation and translation the driver's telling it to. But this wheel can't go at 1.5, it can only go at 1. And so physically the robot is now going 0.9 in this wheel and 1 here. And so when all of these vectors come into play, the rotation and translation that you will get from the robot physically will not be the rotation and translation that you get, that you asked it to get, because you're going to get capped by your maximum velocity, which is, or maximum power, which is smaller than the maximum power that you're asking for on some of the wheel modules. Does that problem, does anyone have any questions about that problem? Okay. So Alex, why don't you tell everyone how we can address that issue?
So what we did was we put all of the outputs, like we got the extra big number, and we put it in an array, and then we figured out the maximum, and then we divided all of the all the numbers by the maximum. So whatever the max was changed to 1, like if it was over 1, but if it was under 1, then
yeah, so exactly. So we've got 4 drive motor speeds at any given time, 1 for each module. And so what we would do, what Alex wrote, is that if one of the drive modules is asking for a power of 2, and so let me write this out here a little bit. So if we had velocity, I'll call it speed for module 0 equal 2, and speed for module 1 equal 1.5, and speed for module 2 equals 0.8, and speed for module 3 equals 0.5. Those are totally valid numbers that could come out of the math. But the speed for module 0 and the speed for module 1 are larger than what we can source. And so what Alex did was she divided all of the speeds by the largest speed. So in this case, it would be 2. And so you divide this one by 2, this one by 2, this one by 2, this one by 2. And so you'd get a speed of 1, a speed of, 0.75, speed of 0.4, and a speed of 0.25. And so these would be the rescaled powers that we actually send to the motor. And by dividing it by the largest value, that ensures that we're using motors as much as possible. We're using at least one motor at its full power. And the other ones are scaled now lower than that. Now the one other nuance here that Alex also mentioned is that we don't want to do this if all of the values are below 1. So if you had a situation where you had, we'll say, 0.5 and 0.3 here, we don't want to divide everything by 0.8. Then what you'd end up with is, I won't show all of them, but oh my goodness. Right, you'd end up with a 1 here, for example, and then you'd end up with, let's see, 0.5 divided by 0.8, 0.625, and then this number would be larger and this number would be larger as well. So then when you do the normalization, all of a sudden your robot is going faster than what you asked it to. And so now it's, here you're going slower than what you asked to, but you're going as fast as what's physically possible. Whereas in this scenario, all of a sudden you've made the robot go faster. It's still physically possible, but now it's actually going faster than what you've asked it to. And so you don't really want that behavior either. And so there's a piece of logic in there that Alex put in so that it only does this rescaling if at least one of the requested speeds is larger than 1. So we're at exactly 8 o'clock. Are there any questions or comments about what we talked about today? Okay. Well, hopefully that was helpful. You will all get to vectors at some point. I think when I was in high school, the first time we talked about vectors was probably AP Physics. They may teach it in some other physicses and some calculus classes may also introduce them first, but that's typically about when you'd see it. Oh, so Alex, what class are you taking that's going to cover vectors? Okay, what is your extra teacher? Pre-calc. Okay, awesome. So hopefully it won't, anyone who's taking pre-calc, this will give you a little bit of a bonus there when you're looking at it. What we're going to talk about in the next sessions will be, we'll actually look through the code for how we did the math in the code. Now that we've gone through the math, going through the code itself is going to be fairly simple. So we'll be able to move to that pretty quickly. The next sort of confusing block of stuff to talk about is how we handle converting the goal angle into an angular distance for the PID loop, and how we handle sort of efficiency. So there's multiple angles at there's multiple